In September 2023, a representative from NASA's Kennedy Space Center visited our laboratory. We discussed how geopolymer technology could help simplify human exploration and settlement on the moon. During our discussion, I shared some concerns regarding ongoing research by teams in Western Europe, the United States, and China. While all groups claim to be implementing geopolymer technology, I have observed that research teams working in China seem to most strictly follow the original geopolymer methodology. Others appear to be developing alkali-activated materials instead because they simply mix the regulant simulant in a terrestrial mix of crushed rock, which is produced in order to simulate lunar regolith soils. It is important to recognize the difference between these two material systems. The simple alkali-activated materials form hydrate bonds like Portland cement, producing compounds like calcium silicate, hydrate CSH, and sodium aluminous silicate hydrate, NaSH. Geopolymers, meanwhile, polymerize into an amorphous three-dimensional structure through geochemical processes. This was accurately reflected in the responses the artificial intelligence provided when asked about geopolymer suitability for lunar habitats and construction work in environment. Why? My questions to Claude Instant from Anthropic Artificial Intelligence was, why geopolymers are excellent candidates for lunar habitats and for work to be carried out in space? The answers of the artificial intelligence Claude Instant are given in a heading in red color. Resource efficiency. Geopolymers can be produced using lunar regolith as the raw material source of aluminum and silicon. This allows habitats to be constructed directly on the moon without transporting heavy traditional building materials from Earth. Resistance to radiation. The amorphous structure of geopolymers make them more radiation resistant than crystalline materials like concrete. This is important for shielding habitats from solar and cosmic radiation. Thermal properties. Geopolymers have good thermal insulation ability, which help maintain a stable interior temperature within habitats subject to temperature swings of over 100 degrees C between day and night. I already mentioned yesterday in my keynote on Research and Development 2024 that our Geopolymer laboratory has started a 3-year project to develop 3D printing on high-strength, stable ceramic-type geopolymers. Strength and durability. When mineral fillers are added to the geopolymer paste, for example, with the addition of feldspar powder, they cure in very strong and durable ceramic-like materials that can withstand the temperature extremes and lack of atmosphere on the lunar surface. Their strengths allow the use for structural applications. During this study, we came across a series of metakaolin which have very high mechanical strength. I repeat what I have already said, but this is important, and this was achieved without the addition of fibers. In the literature, that is the mainstream, the flexural strength is 10 MPa. In our lab, for all-purpose commercial metakaolin, like the Metamax, the flexural strength is 15 MPa, and these new metakaolins have a flexural strength in the range of 25 to 30 MPa and a compressive strength of 180 MPa with mineral fillers like feldspar. Lightweight. Geopolymer compositions can be formulated to be lighter than traditional concrete, reducing the mass that needs to transport from Earth. 3D printable materials. This we know. Certain geopolymer paste can be used in extrusion-based printing approaches, allowing versatile on-site construction techniques. Stability in vacuum. Unlike ordinary PC concrete and alkali-activated materials, geopolymers retain their integrity and strength when exposed to hard vacuum conditions on the lunar surface. And if you remember, this is due to the structure, the quaternary structure. There are several reasons for stability of geopolymers in a high vacuum. The quaternary structure of the geopolymer micelles is well defined, and I presented this in my keynote on research and development yesterday. Geopolymer binder consists of these amorphous nanoparticles, and the enlarged view on the screen shows beautiful geopolymer micelles with overall dimensions in the range of 10 to 20 nanometers. Fillers, such as regolith sand and fine aggregates, are mixed with the geopolymer micellar binder system to produce composite materials, cement or concrete, that exhibit all the physical properties that I will now develop in this keynote. Stability of geopolymer in a high vacuum. X-ray diffraction and nuclear magnetic resonance analysis confirm that the 3D network of the polysilate geopolymer micelles remains intact in vacuum. There are several reasons for the stability of geopolymer vacuum. Amorphous structure. Unlike Portland's concrete, alkali-activated materials, the amorphous structure of geopolymers does not allow direct sublimation of water or other constituent on the vacuum. Low permeability. The 3D geopolymer micelle network gives geopolymers very fine nanoporosity in the range of 5 to 10 nanometers and low permeability. This greatly limits water loss in a vacuum. Strong chemical bonding. The bond SiO-Al or SiO-Si are stronger than ionic bonds in cement, calcium, oxygen, silicon, or Nash alkaline-activated materials. The geopolymeric network is therefore more chemically stable in the face of aggression. Limited water absorption. Unlike Portland cement and alkali-activated hydrates, water is not a structural component of geopolymers, but only a reaction carrier. Residual water content is lower. No liquid water. Residual water in geopolymers is either chemically bonded SiOH or in vapor form. It cannot evaporate suddenly in vacuum. No spall. Thanks to these characteristics, geopolymers do not spall or burst in a lunar vacuum, unlike some ordinary Portland cement and alkali-activated materials. Their polymeric network remains intact. Studies have shown that geopolymer samples exposed for several months to high vacuum show no signs of deteriorations. Residual water in the pores sublimate very gradually by various mechanisms, such as diffusion, without damaging the structure. All these properties are not only valid for the moon, but they are also valid for our material used on Earth. Gas permeability of the geopolymers, already very low at atmospheric pressure, becomes virtually zero in a vacuum due to the clogging of pores by the progressive sublimation of water. Repeated vacuum pressure cycles produced no deterioration, demonstrating the absence of bursting caused by the expansion of water during pressure variations. Their high thermal stability also protects them from significant temperature variations in space. Geopolymers appear, therefore, to be particularly resistant to the extreme environmental conditions encountered in the vacuum of space, unlike many ordinary cements. What are the limitations and technical challenges? Artificial intelligence answered. Feedstock variability. The chemical and mineralogical composition of local lunar regolith may vary significantly depending on location. This could impact geopolymer properties, and recipes would need optimization. Water requirement. Geopolymerization requires water, which is scarce on the moon. Water would need to be carefully imported or recycled. This last statement is wrong. An estimation made in 2023 is that there is 2.7 multiplied by 10 exponential 14 kilogram of water, or 2.7 multiplied by 10 exponential 11 cubic meter, 2,700 billions of cubic meters, which are continuously renewed by solar wind impact on the moon, in addition to the frozen ice already detected in the polar regions. This water presence is based on a recent survey published in 2023 by Nature Geoscience with a title, "A Solar Wind-Derived Water Reservoir on the Moon Hosted by Impact Glass Beads," by a team of 6 Chinese institutions and 3 British institutions. I read some excerpts of the summary. The past 2 decades of lunar exploration have seen the detection of substantial quantities of water on the moon's surface. Today, there is little doubt that most of the moon's surface harbors water in one form or another. However, the origins of this lunar surface water and its spatial distribution and evolution during regolith gardening remain largely unknown. I read the definition of what is gardening. It is nothing to do with garden. I read the definition of gardening given by NASA. Gardening refers to the mixing and disturbance of the top layers of lunar regolith, that is the soil, that happens when impact form new craters. And the regoliths are dispersed, and they move from equatorial to polar spaces. There are several potential sources and processes that could have contributed to the water inventory at the surface of the moon, such as solar wind implantation. It is generally thought that solar wind hydrogen ion implantation could react with surface minerals to produce hydroxyl or water in lunar soils. I read, this is all the extract of the abstract. The surface water produced and or delivered on the moon's equatorial regions may migrate to polar regions driven by temperature oscillations. Here we report the abundance, hydrogen isotope composition, and core-to-rim variations of water measured in impact glass beads extracted from lunar soils returned by the automatic Chinese Chang'e 5 mission in December 2020. The impact glass beads preserve hydration signatures and display water abundance profiles consistent with an inward diffusion of water, wind-derived water. We estimate that the amount of solar wind-derived water hosted by impact glass beads in lunar soils may reach up to 2.7 multiplied by 10 exponential 14 kilo. However, this is not molecular water, H2O, but hydroxyl groups in SiOH. Hydroxyl groups in SiOH, like geopolymers, hydroxyl groups. And this solar wind-derived water, or hydroxyl SiOH, is continuously, every day during the lunar days and depends on the intensity of the lunar wind. I continue. The earliest scientific dates of 1966 by a group of American scientists with a paper titled Proton-Induced Hydroxyl Formation on the Lunar Surface by A.G. Steller and his team at the Brookhaven National Laboratory in the USA. I read. The interaction of both the particle and photon component of the solar wind with the lunar surface material is expected to produce diverse chemical reactions. Experimental evidence for proton-induced SiOH formation was obtained by bombarding a glass chemically similar in composition to common silicate minerals with high energy proton H+. Here we have the proton H+ from the solar wind. The solar wind contains a lot of the proton H+, which hits the silicate minerals. The first step, we have the attachment of the proton H+ to the lone electron pair of the siloxane oxygen. And the second step, after several reactions leading to the decomposition of the oxonium complex with the formation of the silanol unit OH continuously. Once formed, the OH is permanently bound to the lattice. This specific property is also found in our man-made geopolymers, where the chemically bound water is actually in the form of hydroxyl SiOH or ALOH structural units. We used our geopolymers to produce ceramic type material, and you see the dimensions of the materials, 0.7 millimeters of the thread or 1 millimeter compared to €1 coin. Once formed, the OH is permanently bound to the lattice. Our experience in the synthesis of high-tech geopolymer ceramic materials shows that these hydroxyl units, SiOH, ALOH, release molecular water, H2O, only at medium temperatures in the range of 200 to 250 degrees C. So we have two SiOH, and we can get the water, and we have the reticulation of the SiO-Si system. This exploitation of the solar wind-derived water is therefore possible under these conditions. Conclusions. Geopolymers are excellent candidates for lunar habitats and for work to be carried out in space. This has been my presentation and the answers to artificial intelligence and to geopolymer technology and properties. Thank you for your attention.